All right. So today I'm going to be working in idle rather than in our textbook. Because today I am trying to go over for loops. Okay. So for loops this time I'll actually go over them in more detail, and we'll be using them to learn about various approximations of pi throughout history. We'll be focusing on the Leibniz. I think it's the Leibniz approximation, because that uses one of the most common things we use a for loop for besides repeating something, which is the accumulator pattern. So let's see. So first off, the people in the back, do you need me to up the size of this? All right, let's up the size. It seemed low. Yeah, I think I shrunk it last time. The options, configure idle. Oh yeah, it's way too small. There we go. That should be much better. Okay. So first off, let me go ahead and save this. Save to documents, GitHub, Classroom, ITP, for loops examples. .py. Sure. Okay, so I've just saved this in a file. Doesn't really matter what the name of the file is for this one. But we're gonna start looking at, at running this this phrase, hello. Very straightforward to run that, right? And now let's just split this so that we get our input and output on the same side, or side by side. There we go. So we've got hello. Sorry, we've got a command to print hello. It prints out hello. Now, what we learned is that with over the past 2 lectures, that we've got this construct called a for loop. And yes, for those of you who've already kind of gotten this and read ahead, or feel they've got a good understanding of this, they may feel like that I'm kind of going over this very slowly. But I know where students are struggling. So if you're struggling with this, that's understandable. You're in good companies. For loops aren't necessarily they don't necessarily click. But hopefully we can go over this them and kind of show you how they work in good detail today. So for blank in range. And if I say, let's go ahead and make this easy to count with your eyes without having to actually physically count them. Range 5, run, boom. It prints out 5. It does the indented command 5 times. If I were to add print hello, print world, it would go hello world. It would go hello world, hello world, hello world, hello world 5 times, It does all the lines that are indented in there. Now, let's go ahead and start dissecting this statement. There's a lot of things we can do. The mechanics of a for loop are basically 4 parts. 2 parts are basically solid the entire time. You have the for and the in. Those stay constant. You will always have a for and an in. So the format of a for loop is for something in something. Right now, we were just kind of leaving it blank with a literal underscore. But the most typical thing we see is for I, and the most typical thing we see in the first couple of weeks of class are for I in range. So what the heck is range? Range produces a range of numbers, and perhaps we can best see what it does if I go ahead and print out I. So for I in range 5. So what has changed? Instead of printing out hello, I've said I, and I'm printing out I. And if I run this, we get 0, 1, 2, 3, 4. Range, and we can print out pretty much anything we want in Python. Well, actually, let me test that statement. Can I print out 4? Can I? Is that something that I can do, or is it going to crash? Invalid syntax. No, those orange words, those keywords, it doesn't let me print them out. But the other kind of stuff, like range, I can print out what is range. It's a built-in function, class range. What it does is that range, and what about range 5? I popped up with some hints about it. Range 0, 5. Interesting. But let's go ahead and see what the range, it gives you a hint. Range, stop, range, start, stop, step. So what a range does is that it produces a range of numbers for a for loop or some other iterator to go through. The format for pretty much all ranges that we will be dealing with Python, with one exception, which is when we're doing random numbers. The range for all numbers in Python, basically, if you've got a range, right? So you may have seen this this format in your algebra classes or whatnot, like 5 to 10. This is all the numbers from 5 to 10, right? And then you can also have 5 to 10 exclusive, right? This is all numbers from 5 to 10, excluding the endpoints, meaning it's all the numbers from 5 to 10, but we don't have the 5 and we don't include the 10 in that. It's all the numbers in between. Computer science, the ranges, and again, this is the case for everything but random number generators. Don't know why that's exclusive. I don't know why, but the range for number, anytime we do like a range of numbers in Python or in any programming language, it's going to be like this. The start of the range, the stop of the, yeah. Let me go ahead and start, stop, exclusive. We start at some point and we go up to, but we don't include that last point. By default, we basically only specify where we're going to be stopping. And by default, we're going to be starting at 0. Now, now there is actually a reason why we do this. And I'll show you later as we do more complicated range statements. But the reason is, or rather I'll demonstrate it, but the reason is because it makes it mathematically easy for us to figure out how many numbers are in this range. Because ranges are only about integers. There are no floats for our ranges because that would make things needlessly complicated. I mean, just to simply put, and to demonstrate, how many numbers are there between 1.0 and 2.0? How many numbers are in between them? An infinite number of numbers are in between them. There's also an infinite number of numbers between 1 and 1/2. So yeah, again, we're avoiding existential crises and keeping things simple by just simply having this be a range of integers. So range 5 produces the range 0 to 5. And what this does is that the for loop, when presented with a range, is that it will go through, what it's going to do is that it will go through whatever it's given sequentially. In this case, we're given a range. And so we go through the range one at a time. Remember, the range is all the numbers starting from 0, because 0 is the default starting point, up to, but not including 5. 0, 1, 2, 3, 4, which incidentally is a total of 5 numbers. So that's how I know when I say range, it's going to run 5 times. So again, if I do 10, it's going to go 10. Now we can mess with the range a bit. Again, I remember I said like 0 is the default, but there's nothing stopping me from again, let's go to 5 again, so it's easy to see on our output. There's nothing stopping me from specifying a starting point. If it's given 2 numbers, it will know that basically that I should start at this point and go up to, but not include 5. So it's all the numbers from 2 up to, but not including 5. So 2, 3, and 4. That's 3 numbers. And if you weren't sure how many it was going to produce, this is where the math comes in. You can take the stopping point and subtract the starting point, and you'll get how many numbers you get. So for instance, if I have 15 numbers and I'm going to start at 7, How many numbers are there going to be? I don't know, but I will simply just use the math. 15 minus 7 is equal to 8. So there's going to be 8 numbers that are printed out. 7, 8, 9. Oops, sorry. 7, 8, 9, 10, 11, 12, 13, 14. 7 up to, oh, but not including 15. So again, what for loops allow us to do is go through sequences. We can completely ignore the whole going through stuff and just use it also the way we've been doing to just repeat something a certain number of times, which is also useful. But we can also iterate through things other than ranges. The other thing that we've learned that there's one other thing we've used that we can iterate through. For letter in hello. Again, this loop went through any number in the range. Here I'm using letter. Now the variable we can name it whatever. I'm using letter here because it makes sense. I could name it I or L, but I chose to name it letter because it makes sense. So I will go ahead. So it printed this, which was this output. And then for each letter in this, it went through sequentially. It printed out H, it printed out E, printed out L, printed out L, printed out O. That's fairly useful. But why? Why do we care? Well, with words, we'll see that we care very much. But for numbers, this allows us to do math and accumulation stuff with math and lots of various operations with math. For instance, the most common pattern you'll probably be using that involves for loops is something called the accumulator. And I'll go ahead and make the math not horrendous by doing this. And now suddenly it gets all scary. It's okay though. Gives us 10. What in the world just happened here? Well, I wanted to know what the range of numbers from 0 up to, but not including 5 was. We had the following, so range 5 is composed of the following numbers, right? This is composed of the following numbers: 0, 1, 2, 3, and 4. The total of all of them together is, well, we can ignore this. This is 5, this is 5, 5 plus 5 is 10, right? So what does this do? Well, we start out with I is equal to 0. And total is also equal to 0. Right? And so what we do first is we say, okay, let's take total and I, so 0 and 0, add them together, 0, and store it in, and then that gets stored in total. Okay, so in other words, much ado about nothing there. Okay. Next, though, what are we doing though? We update, we go to the next number in the range. We go to I is equal to 1. And so now we have 0 plus 1. What's the sum of 0 plus 1? My kid loves asking me questions like this. It's equal to 1. He's fascinated that adding anything to 0 gives you whatever you added. Okay. Next, the next number range is 2. So we do 1 plus 2, which gives 2. 1 plus 2 is equal to 3. We then take that number, and remember the assignment, this is the assignment statement. It means we take what's on the right and store it on the left, which means the total gets updated to 3. I gets updated to 3. which means that now we've got 3 plus 3. Take that, 3 plus 3, stored in total, that makes it 6. Let's clean it up a bit. So we've got I is equal to 3. So we just finished up with I is equal to 3, which gave us 6. Now we update I to the last number, which is 4. And we have 6 plus 4, that becomes 10. So we are going to store 10 inside of total. And then we print out what the total variable, we asked to print out the total. We get 10. This is kind of fun to be able to do that and kind of do that sequentially. But this is what's called an accumulator, where we keep going through, we iterate through something. Iterate that's what we are doing with the for loop. Iterate means to basically move through all elements of a sequence. We iterate through all the numbers and add them into this one at a time. So this is kind of useful. The range isn't, there is one more thing I can do with the range, right? I can do 1 to 5, right? And start at 1 instead here. And then all the numbers from 1 up to, but not including 10, which would be 45. Okay. But then I can do some, there's one more thing I can add. I briefly mentioned it and then like flew by it, and that was called step. So there's a third variable you can do there. And let's go ahead and comment this out and print I, and then we'll put in our step variable. And I'll just put in 2 over here as our step variable. Very interesting to see how what this works, but it's fairly easy to figure out what it's doing, right? First, let's do it without the step variable, just so we have a baseline for comparison. It printed out 0 at the end because total is still 0. So let's go ahead and ignore that by commenting it out. But we've got 1 through 9, which is 9 numbers. 10 minus 1 is 9. So that's how we know how many numbers came out. Now, if we put 2, 1, 3, 5, 7, 9. By default, your step variable is 1, meaning that you go from 1 to the next number, to the next number, to the next number in the sequence up by 1s. You're counting up by 1s by default, right? Here we are counting up by putting in 2, we'll count up by 2s. By putting in 3, we'll count up by 3s. And if we put in 3.5, I believe it should be very upset about this. Yes, it gets very upset about the fact, right? We're just dealing with integers here. Okay. Something that you might find reason to do is sometimes you might need to go through a sequence backwards, and the step also allows you to do that. It's less common. And this will be very interesting. So this is start at 10. The range is to 1. So it's going to go down 2, but not include 1, right? You don't include the second point, and you're going down by 1s. Right? And it stops at 2 because the range, we explicitly said up to, or rather down to in this case, but not including the 1. We don't include this endpoint. Okay, that rarely comes up, but it's worth mentioning that you can do stuff like that. Most of the time, you're not going to use the step variable, but it's worth mentioning because it exists and can make your life easier rather than trying to do some annoying math. Okay, so the for loop is extremely powerful. We can do things with it, by the way, to like, we can do fun things with it with like turtles, to like make turtles gradually change color, or to make spirals. Like import turtle, and Bob is equal to turtle. Okay, and don't worry about trying to frantically copy down. I should have mentioned this earlier. Don't worry about trying to frantically copy down all this code. I'll do my best to try to get it to all y'all via GitHub or something like that. Or worst case scenario, you can always just post it on Discord, right? But I try to get these things on the GitHub. So you don't have to worry about frantically copying it down. Okay, so Bob is equal to turtle. I make a turtle. And then what am I, because I'm also, if you haven't noticed, I'm doing a lot of editing on it, adding and deleting, which makes it, you're like, I just finished typing that, but now you're deleting it. Yeah, so chill, try experimenting on your own, it's fine. So now what we can do is we can say, typically we tell Bob to do stuff like move forward a certain distance, like 50. Instead of that, I'm actually going to be explicit and say, hey, or rather I'm going to use a variable. I'll say distance. I need to create that variable, of course. Distance is equal to 50. And now, right? So let's see with the for loop that we've been using previously. For blank in range. Let's do this 20 times. Okay, for blank in range 20. So this will repeat 20 times. It produces the range 0 up to, but not including 20. But but the blank means I don't care about the numbers. Right? I don't care about the individual numbers right now. Move forward the distance, and then Bob dot, let's say left turn, Bob dot left 90. And we'll run it, and Bob's essentially just going to go in circles a lot. Let's go ahead and actually, yeah, so he's going to go and run in circles, right? Or rather in squares, I guess, because it's a square, right? He's producing a square. I know it's very tiny on the screen for everybody. I promise this is going to stop being an issue because I'm what I'm about to do. Instead, so what we can do over here, and this is a lot of fun, is I can assign a variable, I, and then I can do plus I, and this is going to be very hard to see, so I will increase it as we move on. So I can do distance plus I. It's a bit hard to see here, but you can kind of see it's creating like an outline and a little bit thick. What is going on here? Well, the first line he draws, he moves forward distance, which is 50. I'll go ahead and switch it to 100. Plus 0. Right, the range is 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 20, but not including 20. So first step, he's moving forward. He's moving forward 100. Then on the next line, he's doing 100 plus 1. Then he's doing 100 plus 2, then 100 plus 3, then 100 plus 4. Let's go ahead and accentuate this by multiplying the amount that gets added by 10. So instead of 100 plus 1, so it'll be 100, 110, 120, 130, 140. And that just makes it a bit more easy to see. And suddenly we've got ourselves a spiral of sorts, which is pretty cool. Right? So let me just draw for a second, just to reiterate. This first line was the baseline. It was 100 plus 0 times 10, which is plus 0, so it was 100. This line was 100 plus, and now I was equal to 1 at this point, so it was 0 plus 1 times 10. 1 times 10 happened first because of ordered operations. So this was a total of 110. It was 10 pixels more, then 20 pixels more, then 30, and then now it's very apparent this is 40 pixels more than the original one, right? So it just keeps going and going and going. So so this is actually kind of useful. And something like this, like asking you to draw something like this is probably on the upper end of difficulty that I would ask on the first exam for drawing it, for like, what the turtle does. And no, it would not have to be exact. You would just have to draw a general squarey, spirally shape, You wouldn't have to like say, oh, it's got this one, this side has to be 10, this side has to be 20, and no, it's just got to be in general that you understand what the code is. Okay, and I've also decided that our first exam, just because it allows me to ask easier questions or less intensive questions, the first exam will be on paper. Okay. But and so that means that we have to decide the note situation. Now, I'm a fan of, when it comes to notes, I'm a fan of two notes. Bring as many notes as you want, don't care how many, or just bringing a single sheet front and back. Both of them have their merits. The merit of the former, bringing as much as you want, allows you to bring as much as you want because no programmer actually truly programs without any reference. Right? That's true. On the second hand, forcing you to bring in one piece of paper front and back does that limitation forces you to prepare a cheat sheet, which forces you to prepare, which means which means I've just forced you to study, which means you might get, might actually do better. I don't know. So I just want to ask informally, like, what do people feel about the two options? One, bring in as much notes as you can, notes being paper, as much paper as you want, or just one piece of paper front and back. What do people feel? Do people feel strongly one way or the other? Sorry? I mean, I don't care if I don't care if your notes are like printed or handwritten, right? A note to me means something you bring in for the exam on paper. Yes. Forward, left, right, back. Forward, left, right, back, and sorry, pen up, pen down. Forward and backwards. Backwards, the turtle just goes backwards. We don't use it too much, and I probably won't use it on the exam, but it's useful because if you want to draw something, like if I ask you to complete code, it could allow you to, not have to turn the turtle around. If you don't feel comfortable saying what your preference is via class, in front of everybody, because that puts the spotlight on you, feel free to send me an email, and I'll take it under consideration. I haven't made a hard decision one way or the other, but keep in mind that you will have some form of notes. And even if I do let all notes, it's still useful to make that even if I allow all notes, it would still be useful to bring in like a consolidated index cheat sheet, then you get the kind of best of both worlds there. Yeah, again, I have the philosophy that basically programmers you've seen how often I look at references to double check my stuff. That's what programming does. But at the same time, I don't want you, I have to balance that out with the whole, well, I can't let you have access to Stack Overflow because now every easy question I ask becomes not easy, it becomes trivial. Or easy to medium, I should say. Totally. You could totally print out the documentation for Turtle, right? It's a matter of what you want to be prepared for. We'll discuss that in more detail. But now that we've got kind of an idea of how this works, let's talk about pi, the number. So unlike a lot of your other professors, I don't actually know, but I'm assuming unlike a lot of your other professors, and this is probably a result of me being rather young compared to your other professors, that I'm a big fan of Wikipedia. Especially when it comes to, because when I was in high school, that's when it was started and school started to have to come out with policies about using Wikipedia. And again, with me citing Wikipedia, it's a matter of, you don't do that because it's a tertiary source, and in academic settings, you want primary and secondary sources, but not tertiary sources. But anyway, but it's got stuff like this. It's like, what is pi? Well, 0 to 1, here's a circle. And if we unwind the circle, it ends up a unit, a circle diameter 1. If you unwind it, it's going to end up at this number. It's the ratio of, a ratio of the circumference to the diameter. It comes out to about 3.14159, which is the number you saw me use when I plugged in PyManual. Now, it is, again, an irrational number. That means that it can't be easily defined by fraction, and that as a result, basically, it goes on forever. There's often a joke that basically any information that ever is produced would be encoded in pi. So pi contains all information ever needed for everything. All video games are in pi. So the idea here, though, and you'll see there's a list of people. Why do we care about people when it comes to it? Because getting figuring out what pi was required people approximating it. Now, approximations have a long history when it comes to computing because a lot of times it's just easier for us, rather than solving it, we approximate it, which means we get some answer that's close enough with a little bit of error, but the error is so small that we don't care about it. So the approximation for pi, it really exploded with computers, but like you still got a decent number. This chart is logarithmic on this. So we still got so as you can see, 100, 10 to the 4th, 10 to the 6th, 10 to, so there was still a lot of progress for digits with, when you're still in the handwritten era. Chinese mathematics, this was approximations correct, corresponds to about 7 decimal digits. So there are some different approximations of pi that were used for a while. Let's see. 256 over 81 was one approximation that gave basically divide those two numbers. It gave you about 3.16, which isn't 3.14, but it's good enough for some large stuff, I guess. Another one was that some Egyptologists claim has been met with some skepticism, but 22 divided by 7, that gives you 3.142. It's 3.1415, right? But it's 12, so this is like close enough for elementary school, right? In elementary, middle school, you would use 3.14. This is plenty good. There's other ones. Archimedes used sharp inequalities to prove that between these 2 points using shapes. It was one, yeah, I like this one. This one, which was done by a Chinese mathematician, let's see. Yes, 355 divided by 113. These were very, very good. The latter fraction is the best possible rational approximation of pi using less than 5 decimal digits in the numerator and denominator. In other words, that was the easiest, that was the most accurate approximation that a human could reasonably remember. 355 divided by 113. Because if you need to remember things, generally you're trying to remember, memory is basically limited to like 4 to 7 items. That's 6, so that's at the upper end of where it's reasonable. Now once we got to the Middle Ages, we got to where we're going with this, which is that eventually we got to infinite, to sequences, converging sequences. Basically, what is a converging sequence? If you're not taking calculus 2, you probably don't know, but basically that means we have some equation, we keep adding numbers, and as we add numbers, we get closer and closer and closer and closer to our result. And this is the one that we're focusing on today, the Madhava-Leibniz sequence. It's also called the it's often referred to as Leibniz because Leibniz gets named after everything, and naming in mathematics is its own kind of topic that would take up its own lecture. Because not just one person ever discovers one thing. The world was big and telecommunications didn't exist. So you had multiple people discovering multiple things at different times throughout history. And then you discover that somebody else had already discovered it, but it was already famous for this person. It's a mess, is what I'm saying. Okay. So the idea behind the Leibniz formula is that if we keep adding these fractions in a pattern, 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, if we keep doing that, eventually we're going to get close to the number pi over 4. And I can just we could demonstrate that on using Python. Just basically saying, hey, 1 minus 1 over 3 plus 1 over 5 plus 1 over 7, sorry, minus 1 over 7, it alternates, right? Plus 1 over 7 minus 1, swear. All right, So this gives us 0.834, and you're like, that's not pi. Remember, it's converging to pi over 4. So what I'd have, and pi over 4, well, let me go ahead and see. Import math. Math dot pi. Math dot, or is it math dot pi? See, even I forget. And even I misspell. And hit the wrong keys. I'm doing a great job of showing you that basically errors are expected at all levels. And so this is pi, 3.141. So if I do math dot pi divided by 4, I get 0.78. So this is getting pretty close. And the idea here is as I add or subtract terms, minus 111 plus 113 minus 115, I get closer and closer to the 0.78. I'm already accurate to the 0.7. Now, the idea behind this is that, right, this isn't a target number I'm trying to hit. So 1 is way too much of an estimate. So we shave off 1/3, which gives us 0.66, which is a bit too small. So we add a bit more. So we add 0.2 to 0.66, which gives us 0.86, which is still too big. So we keep subtracting and adding, and we just keep shaving off and adding little bits of the number on and off as we get closer and closer. And the idea is that if we can do this infinite number of times, we can get the pi over 2. Or we can just simply do it enough times so that the answer we get over here is the same as over here, because again, pi goes on for an infinite sequence. This isn't infinite. This is much less than infinite, but still a lot. Right? Now, this is because your computers, especially when it comes to floating point numbers, specifically IEEE double precision floating point numbers, these have specific formats which allow them to have they basically have a specific maximum bit size, meaning they can only take up so much space, and therefore they have like only so many significant figures, which this is basically as high as we can store without going into special file formats. So, and since that's how we do the majority of our math, we don't really have to worry about, you know, if we get to that point, we don't really have to worry about it. We're not going to get to that point though. So what we're going to do is that we're going to write a for loop that basically produces this for us. Now, that's a bit tricky because we have multiple steps that we have to do for that. Let's go ahead and go to the whiteboard for a second. No, not over there, because that's terrible. You wouldn't be able to see, and certainly wouldn't get in the recording. Okay, instead, we are going to go to the whiteboard, and we are going to just simply, so we want to encode this sequence, plot 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. And this actually is broken up into like 3 parts but when we look at the 3 parts at the combination of 3 parts, it looks really complicated. But let's look at the 3 different parts. The first part is that, well, let's go ahead and simplify this 1, shall we? 1 over 1. Aha, now we have a pattern. The denominator goes up by 2 each time. Forget about the minus and pluses for a second, because that's another part. How in the world do we flip the numerator, the sign of the number from positive to negative back to positive again? We'll go back to that. But you've already learned it. It's just a matter of figuring out how to apply it in a computer setting. So, but for this, well, I don't know how to necessarily add numerators, or sorry, add 2 on numerators, how to do go to 1 over 2, 1 over 1 to 1 over 3 to 1 over 5 to 1 over 7. But we just learned how to go from 1 to 3 to 5 to 7 to 9, right? And then adding it all up. That's the accumulator. So let's go ahead and just start. Our first task is gonna be, and let me go ahead and go and create a new file so that we have a blank slate to work with. Okay, what we're going to do is that we are going to, let's go ahead and again, work on this task by task. I don't really care about like doing addition right now. The first task is, right, we had these numbers where the denominator went up by 2. So instead, let's just first focus on getting the sequence of 1, 3, 5, 7, 9, as many as we want, right? So let's go ahead and basically set, so first off, for I in range, well, let's go ahead and write down 5 over here. And remember, if we put down 5 over here, we can just, and again, for loop looks like this. Print. Hello, this works 5 times, right? Right, and Leibniz. Okay, works 5 times, prints out hello. And if I switch this to I, it prints out 0, 1, 2, 3, 4. So now I'm going to do one thing to make my job a little bit easier so I don't have to remember stuff. I'm going to create a variable called terms is equal to 5. I'll change that probably throughout our run. And I can just put a variable in there as well, right? That gets it more abstract, but here it's still 5. 0, 1, 2, 3, 4. And if I decide to change this number, I just have to go, you know, I might have a tangle of code later on, but up here I can change the parameters very easily. Like, oh, I need this to be more accurate. It gets more accurate the more terms I have. So I just increase the terms to make it more accurate. So right now we'll go to 5. Okay. So now we get 0, 1, 3, 5. We don't start at 0, right? We start at 1, 1, 3, 5. Right. So like that. 1, 2, 3, 4. And then what we were doing is that we are going up by 2s, right? So 1, 3, but we want like get to produce 5 numbers. So let's see. 2 times terms? That seems maybe. Yeah, it seems right. Just simply because we're going up by 2s. If I want twice as many numbers, I'm going to double the range, right? I mean, we don't need to, but then but I could instead do, if I didn't want to confuse myself by doing that, I could instead say limit over here, right? And I just like and again, it's just names. The name matters to me though, because because I want to be able to view this, you know, a week later and go, what was that madman doing? Okay, so this will be the limit of the number. So we'll go up to 5, but not include it. I'm not going to do terms because that's just gonna, I think that adds a bit too much mental stuff. So now let's do some, so we can now do some addition. So total, right, is equal to 0. And then we're gonna do stuff, and then we're gonna print out our total, right? So what are we gonna do? Well, for right now, let's go ahead and add the numbers. So total, so print out I just to show. And then we will do total is equal to total plus I. So add 1, then 3, and then I print out the total, which is 5. Yes, so 4. I could. There's nothing stopping me from doing that and subtracting, but we're going to want to be able to alternate them, right? Before we do that, I want to get to the, okay, I want to change the next problem. So let's go up to 10. the question was, can I put a minus sign instead of a plus? And yes, there's nothing preventing me from doing that, or multiplication or division. Right. Here we get these numbers 1, 3, 5, 7, 9, right? And we add them all together, right? Print. And let's go ahead and separate it a bit. Print let's go ahead and make a new line over here to separate it from my other output. The total is, just to make it extra fancy looking, there we go. 1, 3, 5, 7, 9. 1 plus 0 is 1. 3 plus 1 is 4. 4 plus 5 is 9. 9 plus 7 is 16. And 16 plus 9 is 25. Good. I was worried I lost track somewhere and missed something. Okay. So we just simply add those numbers. But now, but this problem, right? It wasn't adding 1, 3, 5, 7, 9. It was alternating, which we'll get to. And we were adding fractions. Turns out, if we think about it for a bit, because a lot of times there's hesitation to try to make jumps of logic when you're just starting, but we know what to do for fractions. If we want this to be the denominator, I'm going to change the variable name to denominator. You can keep it I. What is it? Demonimate. That doesn't seem right. What am I going to do? And they say I have to know how to spell things. Joke's on them. Joke's on them. Don't be afraid to spell check your stuff. Okay, for denominator in that, we can simply make I the denominator by doing 1, like printing out, let's do 1, 1, and then, so that would give us these values: 1 over 1, 1 over 3, 1 over, and to actually, do that, it would be 1 over the denominator, right? All I did was just take our value and put a 1 divides before it to make it the denominator. So 1 plus 1/3 plus 1/5 plus 1/7. These together are, 0.5 or like 0.5, and then got, I don't know my fractions off the top of my head, but yeah, that seems about right for that. Okay. Now the biggest challenge. How in the world do I get the signs to flip? Sorry? Yeah, -1. All right, good. Right? If we want to flip signs of anything, we can multiply by -1. So let's go ahead and I'm going to comment everything out for a second. So we have 2 ways of doing a comment, which means to get the code to be ignored. The first is to actually comment it out. And the first is to use a quirk of Python to turn everything into a giant string, a multi-line string that doesn't get evaluated to anything. And it's just a string that exists, and Python reads it and ignores it because it doesn't store it anywhere. It's a quirk of Python. You can effectively think of this as a multi-line comment, though, in many regards, where basically it's just simply saying, this code doesn't exist anymore. You do 3 quotation marks or 3 single quote marks. And so now that code doesn't exist anymore. It's not going to run. So what I want to do is print out the sign, is change the sign. Sign is equal to 1. And I want to keep changing that between 1 and +1. But we know how to change the sign from the sign from 1 to -1. You multiply by -1 to get -1. And then you multiply by -1 again to get +1. Right, so for blank in range, let's, again, this is some number of stuff. I'll do 6 here. Print sign. And then what we're going to do is that we are going to do sign is equal to sign times -1. Or actually, I'll do it this way. I'll first start with 1, then we're going to change the sign first, then print it out. Okay, so we start with 1, and then we multiply by -1. So we started with 1. We take 1 times -1, store it in sign, and we print out sign, meaning we print out -1. Then we take what's in sign, which is -1, multiply it by -1. And we get +1 and we print it out. And then it just keeps flipping back and forth. Right? Now, those of you who had taken programming before might have considered an if statement, but we haven't taught if statements yet, and you work with what you have. You can do a lot by just doing positive and -1s to flip stuff. So that and now it's easy for me to comment that bit out by taking this over from here and putting it down here. And look, just kind of flipped what got commented out. Pretty cool. So that means over here that we will, so our first term is going to be, so the first thing is that we want to create a sign variable is equal to 1. So our first number is going to be 1. So we want whatever happens, wherever we put this value to flip the sign, we want to ensure that the first value is going to be +1, not -1. Right? So if we're starting with sign is equal to 1, we don't want to put this over here because it would immediately flip it to -1, then we would add 1. Right? Sorry, add -1. So instead, we would want to maybe start with -1 and then immediately flip it to positive. Or alternatively, we could just, do the flipping after we've done the addition. Either way works. You just got to be mindful of what's going on. And now we can, and now what we can do is we can run this and see what happens. Oh, right. There was one more thing we have to do. Total is equal to total plus 1 over the denominator, but it's not 1 over the denominator. It should be either 1 or -1, which would be the sign. Yes. This? Yeah, yeah, it's like casting. It's kind of like casting, but I'm more converting it. This is a way for me to basically make it a bit more easy to see. And now I can do some. Yeah. Yep. And now I can do, yes, it makes sense for me to do it like this. So sign is, turn the sign into a string. So now we can see print. What am I doing? Sign, yes, str. Look, talking and programming is sometimes very difficult. Str, let me go ahead and open this up. Str, so we have the sign plus the slash plus the number. So we get either positive or -1, then we have the slash, and then we have the number. And then we add that value to this. So we get 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, right? And so now let's go ahead and check how our answer compares to the actual value, which we'll do by importing math, which imports all sorts of useful math values and operations. And then below here, just to kind of make it easy to compare, because it will put them right on top of each other, and because I'm using a monospace font, it will be easy to compare each digit to each other digit. Print math.py divided by 4, which is pi over 4. Right? Okay, that gives us pi over 4, but honestly, like, you're more familiar with pi than pi over 4, so let's swap that, right? If I want to instead compare the values to pi, right, this approximates to pi over 4, so instead I could, get rid of the over 4 and multiply the actual total we're getting by 4. And that would go from approximating pi over 4. So pi over 4 times, our approximation of pi over 4 times 4 would now be an approximation of pi. So we get 3.339, which is not 3.14, but we've only added 5 numbers, right? We've only added 5 terms, right? So let's go ahead and increase our limit so we have more terms. Let's go ahead and instead do 100 terms, because that's way more than I can do by hand. And now we see where, like, even in this amount of time that we spent programming, right, we probably couldn't have gone up to 1 over 100 by hand. It's just a lot of work to do that. And now we get 3.12. Although it's very interesting, right, that we get 3.112159, that like all these digits are, all but the middle, what this middle digit are correct. It's a very interesting kind of coincidence, in my opinion. So now if I do 1,000, I'm going to run it, and we're also going to learn something. Printing takes a long time. Printing is actually a very expensive, is actually a time consuming operation for your computer to do. So we can just simply not print out stuff, by just, again, commenting it out. We don't need it anymore. We know it's flipping and it's producing the right numbers. So now we run it, and runs like that, because it doesn't have to worry about printing and moving things off screen anymore. So now we can actually up it by maybe 100,000. And we see that when we get to 100,000, first off, it's working very quickly. And we've got 3.14157 instead of 159. Okay, so, and maybe if we have it go to 1 over a million instead of 1 over 100,000, sorry, 1 over 999,000, so 999, because we don't go up to the million. And now we get something that actually that's actually very accurate, which is 3.14159. Would take us a long time to do that by hand. But eventually, even this will have its limits. Right? Again, I just typed in more zeros. I'm having it run 1 billion times versus 1 million times. And it will take a while because, I went from 1 million to 1 billion, which means this program's going to take 1,000 times longer. And when we were doing it earlier, it wasn't actually taking so long. So multiplying our time didn't really matter. It's still going. It's not like in an infinite loop, which is something that we'll discuss briefly before, which is worthwhile. So I'll just terminate it. This program is running. Do you still want to kill it? Yes, it's dead to me. So 10 million though. Yeah, it's able to do 10 million, and if you could see that there was a hesitation there, right? Hesitation versus if we were doing 1 million as our limit, there's like this merest bit of a hesitation. And now there's 10 merest bits of a hesitation. And now there's 100 merest bits of a hesitation. Which adds up. That was good timing on my part. All right, so it takes a while. So these things take a while. Now, with for loops in other languages, you often have, less so in Python, you have to worry about you occasionally have to worry about something called an infinite loop. So for instance, let's go ahead and open up this for loop over here again, Back over here where we were drawing stuff with our turtles. Right, you may have noticed that in this textbook, it protects against infinite loops from crashing your browser by having a strict time limit for how long things are allowed to run. Over here, total is equal to 0. Print the total, right? We're going from 1 to 10 up by 2s, right? On the other hand, what if I said to do 1 to 10 up by 0s? Well, fortunately, Python's clever and protects you. It says argument 3, which is the step 1, should not be 0. Protects you like that. I can't do stuff like 0.0 because it also protects me by having to do all these values have to be floats. Those are integers. Because floating point arithmetic is messy. Like, let me demonstrate very clearly to all of you how messy floating point arithmetic is. Okay, it's very simple. This works for every single programming language in existence because they all use the same format. 1 plus 0 plus 2.0. 3.0, right? No surprises there. All right. Dumbest magic trick in the world. 0.1 plus 0.2. What is that value equal to? 0.3, right? Wrong. It's 0.3 and a bit. Because and the easiest, now you can look up on Stack Overflow and stuff for very technical explanations about this. But it has to do with the fact that we're not storing 0.1, the decimal value. We're storing 0.1, the binary value in bits, right? There are numbers that base 10 has trouble encoding, for example, and the same extends to base 2. What do I mean by that? Well, for instance, let's take a look at this number. Try throwing that into your calculator. What does it come out as? 0.3. Okay, now on the flip side, if I throw this into a calculator, 2 divided by 3, what does that get? 0.6. If you're using a calculator, it might decide to round to give you a 7 for the last one. Like base 10, which is the number system we use, has trouble dealing with this kind of stuff. Similarly, base 2 has its own troubles, and there's just some kind of little bit of error there when that happens when converting, and this is the smallest amount it can display as an error in that case. Just is. That is basically everything I told you was a lie, but it was a lie that's accurate enough. Okay. The point being is that a lot of times when you're dealing with decimal arithmetic and stuff like that, like some of you saw that with your temperature converting program. If you demoed to me, I asked you to convert Celsius to Fahrenheit, right? And I would give you 37 degrees Celsius, and that should be 98.6, right? And if you're ever a parent and you get those thermometers, you become intimately familiar with these temperatures. 37 for a newborn, great. 38 degrees Celsius for a newborn, terrible. Get them to that's not a good fever for a newborn. So, if I am remembering correctly, I don't know. It's been a while and I didn't get much sleep then. So, but anyway, the point being is that if you converted 37 degrees, that should be 98.6, which is that's standard human temperature, which is a lie. It's not because human temperature is weird, but you would have gone 98.6 0 0 0 0 0 0 a bunch of zeros and a 1, right? It just again has to deal with our arithmetic is messy on those floating point numbers. IEEE precision. Yeah, there we go. Once I started looking up precision, see, IEEE floating point. IEEE floating point, which will direct me to 7.34, which was, there we go. No. Binary 64, which would give me double precision porting format, which is this standard over here. And this is how, in case you're curious, things are encoded in your computer. Again, it's all zeros and ones. It uses 1, 0, and 1 for the sign. And then it stores an 11-bit exponent, an 11-bit, meaning, and bit is short for binary digit. And then this is all the space it has for that fraction. A lot of zeros and ones. Actually gives you quite a huge range of numbers with the way it works. The small, right? It can get pretty small to pretty big. They also use some numbers to encode things like infinity and not a normal. So, sorry, not a number. All right. So for instance, if I were to do 1 divided by 0, I get an error, just like you'd expect I should. Anyway, that was quite the aside. So we've learned a lot today. So let me discuss what's going to happen in the upcoming days. Because as you can imagine, if we've been talking about for loops, we will be working on for loops for, quite a bit. So module 3, okay. Module 3 deals with turtles and for loops. You can probably do a bunch of them without using a for loop, but you need to use for loops for at least one of them, because otherwise it just gets very hard. I don't know if you can create something with a polygonal thing without of n sides without, Okay. Yeah, that was. Okay, so anyway, turtle loops over here, right? That's going to involve using loops. I even put in the name, right? This is module 3. So if you haven't started on Friday, so if you haven't had lab yet, you'll have lab to work on this. Same with Monday. If you haven't had lab on Monday, you'll have time to work on that. The next one, which the due date isn't quite set yet, notice it says lab 4 and 5. That's because it's kind of 2 homeworks glued together. It's lab 4 and lab 5 all glued into one file, because I feel like it's it's worthwhile to hammer this this home. Right? It goes over how to write, because we'll also be talking about how to write functions, which makes your testing of your code a lot easier and how to organize it a lot easier. So you'll be printing the 99 bottles of beer song, doing a multiplication table, summation of squares, and then you'll be doing a bunch of turtle functions. The difficulty here is, you're going to be doing for loops, and you're going to be learning how to write functions, which is basically your own commands. And that is what we'll tackle next week. All right. So with that, I see people getting restless and I have nothing else to talk about. So class is dismissed. Yeah. Wait. Sleep. That will be okay, sorry, I've got some chat. Okay. I'm gonna end this.